Hi, everyone. My name is James Prestwich. I'm going to be moderating this panel. I'm co-founder at Storj. This happened accidentally about 5 years ago. So I worked in distributed storage for about 3 years. I got to be friends with a few of these guys. I've been kind of hands-off for the last 2 years, so looking to provide a bit of background, get updates on where everything's at. We're going to start off with each project. David from Saya, Sam from Arweave, and Aron from Swarm, giving a quick 5-minute introduction of what Saya, Arweave, and Swarm are. And then we're going to get into a bit of panel discussion, mostly focused around Jakob's questions from his presentation, trying to get a little into the differences and similarities between each of these projects. David, do you want to start?
Sure.
We got this nice little clicker thing.
All right, so my name is David Vorick. I am one of the co-founders of Saya. We've been doing decentralized cloud storage since 2014. And I think we have a very sharp take on the decentralized cloud storage space. So the reason that myself and my co-founder, my co-founder dropped out of college. I straight from college went in to do Saya as a business. And the reason that we gave up cozy lives at Google to pursue decentralized cloud storage is because we felt that we had a strictly superior way to store data. So we felt that we could save 90% versus what you might pay on AWS. We felt that we could do this at full speed. So any internet connection could be saturated, even with the cost savings. We thought that we could get latency down to sub 50 milliseconds to any city in the world. Amazon can do that to their primary cities, but if you're in say Kansas City, it's not nearly as fast. And then we could do this with no downtime, no central point of failure, and give you just automatic resiliency just baked into the low-cost service, automatic resiliency to extreme events such as all of Europe disappearing. So we felt that this was worth pursuing, and so we did. We've been doing this for 5 years. So the core strategy that we use is basically the same as stated in our 2014 white paper. We want to build reliable storage on top of a collection of untrusted hosts. And so the idea is that even though each individual host is not trusted, collectively, the chances of all of them failing is extremely low. And so because they're untrusted, we're going to use encryption. We're going to encrypt the data. Everything's done client-side before we send it to the hosts. We use Reed-Solomon coding to essentially spread out the redundancy. So for what this means is we can do something like a 10 of 30 redundancy scheme. And so you take a file, you break it up into 30 pieces. Of those 30 pieces, you only need 10 to recover your original data. And so this has a 3x overhead. It's the same overhead as a 1 of 3 scheme. But if you assume that each host has a 10% chance of failure, in a 1 of 3 scheme, you have a 1 in 1,000 chance that you're going to lose your data. In a 10 of 30 scheme, it's actually 1 in 1 quintillion. So that's 15 zeros. So this gives us extreme reliability and redundancy, even though our individual hosts are actually pretty terrible compared to Amazon. We incentivize everything on a blockchain using smart contracts, and then as the network is running, we just actively replace hosts who disappear. So if you're storing data on 30 hosts, 3 of them go away, you'll actively replace that, get three more, and repair your data. So the founding principle of Saya is that we're going to be fully decentralized. So today, on the Saya platform, if the whole Saya team disappears, there's no change in performance. New users can still join the network, you can still upload, you can still download, it's going to be full speed. Our presence will not be missed if we disappear, other than the fact that the network will stop improving. So we have no method to access data. We have no method to, one thing that's very important to us is that we can't force push an update onto the network. So the software, every software update has to be manually installed by users. And this really limits the amount of control that we have over the data. We feel that this is super important for a truly decentralized ecosystem. And then finally, it's up and running today. It's been running since 2015 at various service levels. The quality that we've reached today is that we have up to 20 terabytes of storage per node. So you can, that's most people, that's all of your personal data. Upload and download speeds are about 200 megabits per second. And then if you want to download a file, it takes about 1.5 seconds for that download to get started. This will be improved. And we have something called seed-based file recovery. So basically, you can take a snapshot of your data and make it such that this snapshot can be recovered at any point in time while the file contract is still active, using nothing more than your wallet seed. So with just your wallet seed, you can recover up to 20 terabytes of data. And finally, we are a developer-facing platform. We offer a API and an SDK where you can interact with Saya and use Saya as the storage layer for your application. So you can check us out at Saya.tech if you want to download the software, and Saya.tech/docs is where you can get the you can see the API and you can browse our API. It says questions. I believe that the whole panel will do that. So.
We'll take good. All right. Sam, want to take the next? That's what the slides say. Great. Thanks.
All right, cool. Okay, hi everyone. I'm Sam, one of the co-founders of the Arweave project. Arweave is a decentralized storage system, but it's a little bit different, I think, than Swarm and Sia, in that what we're focused on is durable, long-term storage of files. In fact, actually truly permanent and persistent storage of those files. In a mechanism that is essentially close to an archive rather than a file storage network. So the critical technology at the base of this is a block weave. The idea is take a blockchain, but instead of just including the hash of the last block in the production of the next block, we also include the entire contents of a randomly chosen previous block from the network in the production of that next block. This means that if you don't have access to that old block, you can't take part in the mining. And so miners are incentivized to store copies of these blocks and essentially persist the data in the network. The other component of this is that when you join the network, you only need to download the last 50 blocks in order to get started. So you're essentially just rewarded proportionately to the contents that you store. So this is the sort of base layer that allows for storage in the network. And on top of this, we have an incentivized data distribution layer, which is pretty similar to BitTorrent. The idea is, if you give me data, I'll give you data. And then we occasionally give data to each other just randomly and see what happens. And the equilibrium when you do this is just everyone gives data to everybody else all the time. This is actually how you get to the point where 50% of the internet's traffic is BitTorrent. On top of this, we also distribute new transactions and new blocks associated with, or proportionately to one's rank in everybody else's peer list. So essentially, you're incentivized to be at the top of my ranking so that you get access to the data that you need in order to be an efficient miner faster. And this essentially ties this secondary incentive, which is off-chain for data distribution, back to the primary incentive, which is on-chain for data storage. So that's the pretty the 30,000-foot view. And the idea is that we make all of this available with basic web technologies. So every node in the system is a HTTP server, and all of the data distribution is done through normal JSON and encoded data. It's pretty simple. The idea being that you can then point a web browser at any node in the network and get it to serve to you the data from it. So what we built on top of this sort of basic storage layer is what we call the permaweb, which is just a layer that allows you to access all of the data inside this as if there was a web inside a blockchain, so that we can essentially get a massive amount of knowledge and history into this network and make it available in a way where there's no 404s ever. That's the basic principle. Thanks. Going that way around?
Can you get me a browser?
What's that?
I just need a browser window.
This is not my laptop, so I do not know.
Yeah, I just need a browser.
Okay. A web browser. Yep. Are you gonna load your presentation from this one right now?
It's up there.
Yeah, I knew when I use it. Can I? Oh, well then.
You can just change the display.
mirror them. Wait, where's the mouse?
The mouse is up there.
How's that?
Yeah, there you go.
Yeah, that looks good. All right, 95.216.
Okay, great. So I'm going to give a very quick introduction to Swarm. Swarm was the part of the initial Ethereum project, data storage and content distribution network to go alongside the blockchain and Whisper, the communications protocol. Let me first show you what it looks like. If you're running a Swarm node, this is the interface you will see. Mostly you'll interact with it through an HTTP API, but if you load it directly, this is what it looks like. If I type in something like the swarm.eth, you will see the website. What actually happened there, the swarm.eth, the string gets put on the Ethereum blockchain where we look up what the Ethereum name service has. That returns a hash. With that hash, we query the peers and you load the site. So that's sort of the first interaction between the blockchain and this network. And yes, you see our slogan, storage and communication for a sovereign digital society. Storage is clear. Communication, because it's also a messaging system, we can use the same network to route messages. And the idea of sovereignty was, I heard the word sovereign in our introductory message this morning. I was very happy about that because it really is a project about having sovereignty over our own data, our own infrastructure, not to be beholden to any operator, be it Amazon or Google or anyone else. So that's very good. Then another thing I'd like to show you is the idea of, so I'm just going to load something called photoalbum.eth. This is a nice little app. It's a photo album. It doesn't belong to me. It doesn't belong to anyone. You see, this content, it doesn't live in my Swarm storage. It doesn't live in somebody else's Swarm storage bucket. It's just there, and anyone can use it. And the reason I like using this as an introduction, because it shows you that these apps in this decentralized space really are different from regular web apps. This is an editable photo album. I can take one of these albums, one of these pictures, and say, I don't want that in this album. I'll just click the X. It'll be deleted. Sort of. It's not deleted. I now have a new album where that picture isn't in it. You see the address change. Now I've got a hash up there because that's the hash of this new album. And I could press this little plus icon here to upload a photo from my local host, and after a while, remove all these photos, upload all of mine. It's now my album, my content. So the form and the content are separate. I'm not going to do that here because it's not my laptop. Luckily, I did it yesterday. And I saved it on the ENS. So test. And hopefully, there'll be some slides. Excellent. So here's some slides loaded off Swarm. And I'll just give the very quick overview of how this network. Thanks. These were, a long time ago, exported from a Google Doc when we were still on Google. But no more. I'm happy to say I've gone Google free. So, Swarm uses the same underlying peer-to-peer network as Ethereum. That's because we started with the Go Ethereum Geth node. We were part of the same code base. So it's the same dev P2P connections between the nodes. The Swarm nodes connect in a Kademlia topology, but Kademlia is often about repeated polling via UDP and getting more hosts, more hosts, more hosts. In this case, Swarm is built around sort of more long-term TCP connections with specific peers, and you stay connected to those peers for a long time and do repeated business with the same peers over and over. That'll be important when we discuss incentives and the discipline of repeated dealings. Files in Swarm, or all data is chunked into little pieces. 4K in the current version. And these pieces are spread out throughout the entire network. So we don't have the hosts hosting the data, or even 5 hosts or pinning nodes or anything of the sort. The data does get spread out. Of course, it's hash addressed. The chunks are arranged in a Merkle tree, and you talk to it by the root hash. But each one of these chunks is stored in the network at the host whose address is closest to it, which means the data is always uniformly spread out throughout the network as much as possible. So we do that for resilience. We're not reliant on any particular host. There's no particular host you can take down to try to remove a file. And on some level, it also gives us nice performance. Like when you download content off the internet, you know, sometimes it's slow, but when you download illegally a TV show about dragons, it goes really fast because many people have it. And there's this whole well of untapped bandwidth that we're trying to tap into, that sort of distributing many hosts, and you're connecting to many, and you can pull all those chunks in parallel, something we heard in the previous talk. That's what we're trying to use. And very quickly, the accounting in Swarm is between your connected peers. I do repeated business with the same peers over and over. So that means it can be much simpler, and we can use, well, let's talk about this later. The one thing I do want to point out is that because all accounting is peer-to-peer, it doesn't have to be Ethereum. We're starting off with Ethereum payments because that's where we come from, but there's no reason two peers can't use any other token, any other blockchain to settle their debts, because it's just hop by hop by hop, and each hop has its own accounting. They work together globally to have the desired properties, but we are allowing different tokens, different networks. That's definitely the vision. We want the one storage network and not one for Ethereum and one for each other blockchain. And I'll leave this one up for last. Thank you.
Sorry, Ron. All right, perfect. Let's make sure this clicker works. There we go. All right, guys. So we've had a little bit about each project, and we had a nice introductory presentation from Jakub from 1KX. Woo, getting a little feedback here. So let's go through kind of each of his points real quick and talk about how your projects address all of these questions about decentralized storage. So first, starting with David, what is your approach to durability? We've talked a little bit about erasure coding and replication. I'm going to assume all of you use both of those things. How specifically do you apply those?
Sure. So I do want to make one correction on the 11.9s thing. So
that's next. That's next.
Oh, all right. We'll come back to it.
We'll get there.
So for durability, yep. So we use specifically Reed-Solomon coding. By default, we use a 10 of 30 scheme, but actually each file has its own redundancy scheme, and when you upload it through the API, you can select what redundancy you want. If you're going to do something like content distribution, you might pick a much higher redundancy to get the file in more places. If you want to save money, you don't, the file is not super critical, you may pick a lower redundancy. So we give, erasure coding. And encryption happens after the erasure coding. So something that's very important in our durability scheme is that hosts are not able to collaborate to deduplicate your data. The way we accomplish this is by encrypting it after we duplicate it, so that hosts have no way to reconcile the pieces without a private key.
Okay, so recap. 30 pieces, any 10 can be used to reconstruct the file, and the hosts who are storing those pieces do not know which pieces are associated with which file, so they can't effectively deduplicate them.
That's the goal, yes.
Okay. Aron?
Yeah, sure. Of course, we've also been looking at erasure coding and Reed-Solomon codes. More recently, we have a project with called entanglement coding. So I'm not the right person to talk about the specifics, but the general idea is this. If you've got two chunks that might be of a different file, if you XOR them together, then that extra XOR chunk is a redundancy that any of the two would give you the third one. And if there's ways you can iterate this scheme over and over that allows you to make one chunk be redundancy for many different files depending on what you combine it with. And there's this entanglement code is about braids of various levels of XORing of chunks. So that gets a redundancy erasure coding that's kind of nicer fit for within the Swarm network than the Reed-Solomon. And it furthermore adds to plausible deniability because each chunk of data can now be part of many different files and is not part of a single file. It can even out popularity of content. So less popular ones become more useful if they're also used as a mask for a popular file, and it does make the analysis of all the network dynamics much easier. But so we use this kind of thing, the erasure coding, whether it's Reed-Solomon or entanglement codes, and there's replication. There's always has to be replication in these networks, I think. Yeah.
So given that your chunks are 4 kilobytes large and 2 to the 4,000 is a very large number, how common is it to actually find useful entanglements?
We have not implemented it yet. So it was presented in May at a hackathon in Madrid, and we've just started working with them to implement these things, so I can't tell you just yet.
Right. It's an interesting idea. Okay, Sam.
So our approach, obviously, we're looking at permanent storage. So from our point of view, durability is, well, the most important thing is the incentives. The way we basically approach this is we say, okay, you give me a megabyte of data, it costs you about a penny. Yeah, and you're paying upfront for around 200 to 300 years worth of storage. And then we put aside those tokens. And over time, as the cost of storage declines, you essentially gain interest on your storage purchasing power from these tokens. And so as long as this rate stays above 0.5% or 1/3%, depending, yeah, you essentially get perpetual incentivized storage of data. Yeah, and of course, the rate's been around 30.5% for the last 50 years. So this is a pretty battle-hardened approach.
Okay, so you're putting tokens up front to incentivize storage of these replicas. Presumably you're using some erasure encoding and redundancy scheme, but the argument is that if you put enough money up front, you can pay for storage forever?
Yeah, exactly. It's basically like an endowment. So it's just interest. Like if you put aside $10 million, for example, and then you want to pay for students' tuition fees at a university, you just pay with the interest.
So does this imply that file storage in Arweave tends to be more of an upfront cost because I have to put down an endowment for an indefinite amount of storage today?
Yeah, you shouldn't use it for temporary storage. It is for permanent storage of information. And you pay for it. Like, it's actually pretty cheap because storage is cheap. So it's about a penny a megabyte. But like, if you want to store something for 30 days, you should definitely use a temporary storage system.
Do you have any guarantee that it won't get deleted if somebody else pays more to store theirs? I mean, is there a negative incentive? Does somebody lose money when they delete your data, or only lose the opportunity to earn payment?
You lose the opportunity to earn payment. So we avoid Sybil attacks from this point of view. So you can't you're not assigning storage to a single person. We're creating an incentive for anyone to come along and store the data, or replicate the data, actually.
So I guess that brings up an important operational difference here. Is it sounds like your access pattern is very different from Sias or Swarms.
Yeah, we're not looking at the same thing, basically.
Yeah, you're looking at long-term archival storage where Swarm and Sia are intended to be used and retrieved more often.
Yeah, I would
that fair?
say so. I mean, the thing from our point of view is building an archive which doesn't have a single central point of failure.
I do want to say we also envision Swarm to be able to be used for long-term storage, but we also recognize that the incentives are very different in that case. So our incentive structure has two sides. One is what we call our bandwidth incentive, which is for the popular content. The other one for long-term storage has very different patterns. And yes, we have that kind of upfront payment that can be unlocked in the future by providing proofs of custody. But on top of that, we want nodes to be able to register on the blockchain with a promise, or just with a signed message that can be proven on-chain, that they will store a content long-term, so that if it isn't available, not just are they not able to unlock payments by providing proofs of custody, they will actually lose a deposit. So you have both the positive and the negative incentives to keep the files long-term.
So we should probably come back to incentives later. And David, I know you're going to have opinions on this when we get there. Right now, one of the things here is that Swarm is the only project here that is not tightly coupled to a blockchain. Swarm uses Ethereum, but is not part of the Ethereum node in the same way that Sia and Arweave are part of a blockchain. That's a fair description?
Yeah, and this actually goes back to Storj, which is kind of interesting, right? Because that is also not coupled tightly to a blockchain.
Right, and they're going to give a workshop later this afternoon. I think Brian is over there somewhere. No? Hey, hi, Brian. All right. Okay, so let's move on from durability real quick, because we've already gotten way off topic on it anyway. So this Amazon 11.9s thing, David, I know you have some. Go for it.
Yeah, so Amazon does not promise 11.9s of availability. if you do the math out, that means Amazon, like 11 nines of availability means less than 1 second of downtime every century, which is not measurable. You can't measure downtime that small, practically. But they do offer 11 nines of durability, which I think is a similarly ridiculous claim. Basically, that means that there's a 99.99% chance that the data will stick around. The chance that Earth gets hit by a meteor, in my opinion, is in excess of 11 nines, at which point it's all gone. So I don't really like and Azure's promising like 16 nines. It doesn't seem like a real metric to me.
11 nines of durability would be 1 byte lost out of every, what, like exabyte, something like that?
Yeah, and the question is like over what time period? I guess, you know, if it's a sufficiently small time period, then it is a reasonable metric. But that's not defined in the claims on the website.
So do you know off the top of your head what they do promise with availability?
I believe it's 4 nines with availability. Yeah, which is also like shockingly, it's like hours of downtime per year or something. It's pretty good.
So my experience with Amazon is that they promise 4 nines of availability or some of your money back.
Yes.
Do you think that, you know, that kind of SLA is something that a chain could provide, or a Swarm or Arweave?
I think that the approach is like we can't do SLAs, they're protocols. It's like doing an SLA with TCP. You've got to get someone else to come along, read the papers, decide what an appropriate economic stake is to put on it, and then do it that way. Like, one interesting approach would be to use Augur or something like that to essentially make a prediction market for the unavailability of data. I think that is maybe the way to go rather than literally giving SLAs. Sorry?
You can have something like insurance of the data where
Yeah, exactly. You're basically creating insurance for it.
it got broken on the downtime.
Yeah, precisely.
Well, our long-term incentive structure, we do call it file insurance, except so the nodes who commit to storing data will have a stake locked up on chain, and when you query it, challenging that the data is not available, nobody can provide the data or a proof of custody. Their stake, most of it gets burnt, it gets destroyed, so it doesn't get paid out to the victim as normal insurance, and that because otherwise the game theory doesn't work out. Otherwise you have an exit strategy. But lost my train of thought.
It works the same way on Saya. So we call them cryptographic SLAs sometimes, and basically, so it's difficult to do that for uptime, but for durability, we can challenge the hosts, ask them if they have the data, and if they don't provide a proof that the data is still being stored somewhere, we can essentially take away collateral that the hosts have posted. And like mentioned, you cannot give the collateral as a refund because then the person who gets the refund has a reason to sabotage the hosts. And like in a decentralized network, we don't want anyone to ever have a reason to sabotage our network. So we destroy things instead.
Yeah, and I remember now. What we're capped by, of course, is the uptime of the blockchain. So we're assuming kind of the blockchain is always there and permanent at 100%, but like that is ultimately the limiting factor for any. I mean, maybe not for data availability, but any dispute, any legal agreement, any smart contract interaction you want to do to prove that someone didn't store data or all that kind of stuff. That's still a limit. So I don't even know if 11 nines are achievable for the blockchain.
Ethereum has definitely not had 11.9 since launch. It had a significant chunk of downtime in 2016 around a consensus failure. The other thing that we kind of assume when we're talking about settling on chain is not just that the blockchain's available, but that I personally can access it when I need to. This is not always the case with chains. We've seen this with Bitcoin and Ethereum fee events in the past. That aside, we're getting a little off topic, Mark. Mark, I saw your question, and we're going to get to audience questions towards the end. I think we have a lot of time left, so don't worry about it. Okay, so let's move on from 11 nines. I think we've kind of settled that we don't think 11 nines is achievable by any human system. Yeah, is that fair?
That's fair.
Yeah. Okay, cool. All right. So David, you touched on this a little earlier, but how do you guys ensure independence of replicas?
We don't. We don't think you need to. We call it proof of access because we think that it's important that you should be able to prove access to the data, that the data is still existing and available. The number of replicas we actually leave to the incentives in the network to basically determine. I think it's a simpler and clearer way to solve the data availability problem, at least.
Okay, interesting. So you're not trying to provide a hard guarantee that there are multiple copies of this. You're trying to demonstrate that it is accessible at regular intervals.
Exactly. And then as part of the consensus, you actually have to recirculate it as well. So it's not just accessible, or not just in existence, but also available.
Right. And I think for Swarm, this is where like entanglement encoding comes in a little bit, is you're trying to have as many different independent copies that are indistinguishable from other chunks on the network, right?
We have independent chunks for the same data, but the key in Swarm is that there's not hosts hosting certain data, but the data chooses which host to be stored on based on its own address. So if, let's say, we're expecting 5 replicas for everything as a minimum in the local neighborhood, if somebody were to mine addresses so that they can have the 5 Swarm nodes with the closest address to a certain chunk, then they would have each copy of that chunk. So we can't guarantee, of course, that those are independent. However, if you are going to be running 5 Swarm nodes, you're much more profitable by spreading them out throughout the network. So the economics certainly goes against that.
Well, that assumes a limited amount of value on the data, right? So if as an attacker I have an expected value of $1 billion by destroying a particular file, then it's not going to matter if I could make 30% more by spreading my nodes out, because my value is in destroying a particular file.
But if that file is properly erasure coded, then you would have to destroy so much of it that you essentially end up with the problem of taking down the entire network. Like you could destroy one chunk or 2 chunks, but if those are not critical to reconstruct the data, then it'll not help you.
So you're saying that, for example, in Saya, we store 10 of 30, right? So we have 30 independent chunks, and any 10 of them can reconstruct the file. So if I'm an attacker, I would need to find a way to delete 21 of those chunks.
In Saya, yes.
In Saya. So I think Aron's argument here is in Swarm, because there are many, many chunks. Each are 4 kilobytes. So a 4 gigabyte file would have 1 million chunks, and then I think another 500,000 of Merkle tree chunks. So you would have to destroy hundreds of thousands of chunks in order to destroy the file in this model.
Well, so the exact how much to have to destroy depends on how much erasure coding has been done on it and how often it's been used as a mask for another file in the entanglements, which you can set it up front to start with a lot of redundancy, but you could even end up getting more from other people using your file as a mask. But the point is, it's not individual hosts. So to take out individual chunks, you'd have to take out whole neighborhoods of the swarm. Right. And so to take out enough of a file, you'd have to take out majority of the entire network, hopefully.
So it sounds like, again, we're primarily managing this through setting incentives in the network.
Well, I would say Society takes 2, I think, cleanly different approaches from either of these projects, which is that the first thing that we do is we encrypt each chunk separately, or each redundant piece separately, which I mentioned earlier. And this gives us a guarantee that as long as someone's doing data proofs, we know that 3 actual copies of the data exist. And we have this like cryptographic guarantee that this data exists in physical space 3 different times. The second thing that we do is we make sure that the person who uploaded the data, their node has control of who ends up with the data. So if there is some network attacker, someone sibling, or any concern about a particular storage pattern, you can simply client-side avoid that storage pattern. You pick where data goes, and that gives you a lot more certainty over how reliable your replication is.
Okay, so because all of these are encrypted independently after erasure coding, they're indistinguishable from other chunks on the network, and you can adjust your own replication factor and encoding scheme, right?
Yep, and you also pick who's actually holding it. The hosts do not have control over what data they get. The uploader has control over what data the pieces, or what hosts end up with the pieces.
Okay, so whereas in Swarm, the chunks choose their own hosts by flowing through the network naturally, content addressing system. I, as the person who owns the file, am responsible for choosing all of my own hosts and managing the redundancy, managing their uptime, and ensuring that my file still exists.
That's correct, and that ensures that there's no way that a host can manipulate the network so that the natural destination of the file is somehow adversarially advantageous to the host.
And then you have some kind of reputation system on top to keep track of who.
That's a much longer discussion, but we have a secure reputation system.
Sorry, I have strong opinions here. Let's move on before we get too into it. Okay, so today I know Saya is live. You're saying people should go use it.
Yes.
Okay, what is the status on Swarm and Arweave?
So we're live. Yeah,
People should go use it.
people should obviously go use it.
Okay.
And the prices are reasonable for permanent storage, but
Right.
that will certainly be more than temporary storage.
And I think
I'd say we're live, go play with it.
go play
Is
with
our
it.
status.
Ah,
The incentive system is not yet live, and we hope to have one with testnet, no real money tokens live by the end of the year. So at least the easiest part of the incentive payments.
Okay.
But the network is stable enough to start playing around and playing with dApps.
okay. So the demo earlier is primarily like the DHT and not the incentive system. Got it. When you loaded up your slides.
When I loaded up the slides, it was loading it directly off the Swarm, but there were no payments involved because none of the nodes have payments
Got it.
enabled yet.
Okay. So 2 of you are live and incentivized. 1 is live, soon to be incentivized. How are prices on Saya and Arweave today?
Yeah, so prices on Amazon are $20 per terabyte per month, roughly. Prices on Saya are $1 per terabyte per month, and then to bring the Arweave 1 cent per megabyte up to the same scale as Arweave would be $10,000 per terabyte per month.
Not per month. That's kind of the point.
Yes.
So,
Yes, important distinction. $10,000 one time. My mistake.
ooh, $10,000 one-time fee.
So if you want to store for over 10,000 months, they're cheaper.
We're not going for cheap. That's not the point.
Just to clarify. Okay. So David is saying that we're underpricing Amazon by a factor of 20. So your prices are 5% of Amazon's today.
That's correct.
Okay. And I should go out and use this right now.
Yes.
Okay,
It's,
cool.
it's on our website. You can download it. It works. The $1 is assuming 3x redundancy, so you can bring it down at a lower redundancy, or it'll go up if you need more replication. But the 3x is what we recommend.
But last time I checked, this was mostly subsidized by inflation fee, right?
No, Saya does not give any inflation to hosts. There's no inflation subsidy for our storage network, and never has been.
Interesting. And so I read around a while ago, we were doing some research, and people appeared to be saying it was just better to mine the chain rather than actually store, because there wasn't enough data to store.
That's correct. So the mining, the consensus building, so we're a proof of work chain. Consensus is built by Hashcash, same as Bitcoin. And the mining incentives are completely orthogonal to the storage incentives. So they're 2 separate systems. And for most of the history of the project, if you're looking to make more than $1,000, mining is the storage system will not get you more than $1,000. The mining system can get you more than $1,000.
$1,000 per
Ever.
Forever. Well, see,
Months.
I think this is a really important part of talking about prices, right? Is what's the utilization on Saya?
Utilization is about 470 terabytes as of this morning, so at $1 per terabyte per month, and that's actually post-redundancy. So at about 33 cents per non-redundant terabyte per month. Was that like $150 per month is the total network revenue, roughly.
Okay. So I could buy out the Saya network with, the one good DAPCon party's budget?
We would be extremely thrilled if you did.
Okay. Do you think prices are likely to stay low if utilization goes up?
Yeah. So basically, we have a network of hosts of unknown depth, but we do know that the majority of the data that could be on the Saya network is turned off just because the demand's not there yet. But we know that if you were to buy out 500 terabytes and put it on the Saya network, and right now, so the amount of live available storage is 2,000 terabytes, 500 of that's consumed, so about 25% utilization. But I have high confidence that if you were to consume, say, 1,000 terabytes tomorrow, I would shoot some emails off and we'd have 15,000 terabytes live in under a week. And I think that the depth of this will probably go for at least 100,000 terabytes before we need to be more serious about finding hosts.
Okay. And so you're saying that there is a huge amount of pent-up supply for distributed storage systems, right?
Yes.
Okay. So you're not worried about prices going up if utilization goes up?
No, and so we've done the math a bunch of times, and every time we've walked through the costs of setting up a brand new data center for storage, we've arrived at using mostly consumer parts, using not too many economies of scale assumptions. We've arrived at a long-term price of between $1 and $2 per terabyte per month. So we think that in the worst case, prices would double, and then at that point, hosts actually have enough incentive to go out and set up brand new data centers to host the incoming data.
And prices doubling is still 1/10 of Amazon?
That's correct.
Okay. Aron, do you have any opinions on how prices will be on Swarm once incentivization is added?
Yeah, so I want to jump in saying we don't know how much the total capacity is or how much is used because there is no global overview in Swarm. The best you can do is heuristics, set up a few nodes, see what the radius of the stored chunks is. So what we find is, what we're aiming at is that to make it really easy to launch a Swarm node just off your laptop. A lot of people have excess storage capacity and bandwidth and would be happy to run, just run it in the background earning revenue. It doesn't have to be somebody running a for-profit data center. So what we like to see is the vision of if this becomes feasible, that you run something at home or on your laptop, and then by serving content to others, you can either then consume content without having to pay an actual currency because you do a service-for-service exchange, or you can just serve, offer the service to Swarm and earn micropayment revenue. That's a great on-ramp, and people used to love running Bitcoin miners on their computers at a loss. It doesn't matter just because you earn some cryptocurrency for fun. So being able to offer storage in the same way to a peer-to-peer network, it could be a great on-ramp for people, and we think there's such a huge capacity untapped in there that the prices are likely to stay very low. Having said,
We're
okay,
good. Startled me.
Having said that, the exact pricing mechanisms and how the network determines the correct prices, that's very hard. It's a subtle point. So we've kind of separated the operations and the routings of the network itself from the price discovery mechanism by setting the clients agree on not a price, but they agree on a blockchain and an on-chain oracle for doing their pricing. And then we can further experiment with all kinds of mechanism design for how these oracles will come up with prices and what kind of metrics they take in. Mm-hmm. But I mean, that's a wide open space.
Right, and I think that brings up a little bit of an interesting point as well, is we've talked primarily about the cost of storage here. Amazon also charges for egress of data. When Amazon serves something to the public internet, they charge the owner of that data. I know that Swarm has a bandwidth incentivization plan as one of its core incentive structures. David, Sam, do you have plans for this at all?
Yeah, I mean, we just essentially use optimistic tit for tat. So you join the network, you share data around, and people share with you because you share with them. But just going back to this mining as an on-ramp. Yeah, sure. So we use a system very similar to optimistic tit for tat for BitTorrent. You just share data with me. If I share data with you, then we occasionally share data with people. It's the optimistic element. But going back to mining as an on-ramp for cryptocurrencies, I think this is actually super, super important. Because like Snowden was saying on, I think it was Monday, there's this KYC cancer that's spreading through the industry that basically means it's impossible to get your hands on any kind of cryptocurrency without also first giving up your passport and driver's license, maybe 2 forms of verification of where you live. And so actually, yeah, having people be able to mine tokens using their resources gives them a way into the ecosystem that is not associated with that KYC. So I think that's actually pretty important.
David, do you have any bandwidth incentivization plans?
We do. So Amazon will charge you about $90 per terabyte for egress.
Which is much more than they charge for storage.
Yes. And then on Saya, the hosts today charge about 15 cents per terabyte for egress. This, I think, is much more a product of bandwidth being essentially available. When we've costed out what a practical industrial scale price is for egress, we come closer to $1 per terabyte. So we're way below that. But I do think that as the network scales up, if we were to onboard Netflix, I think Netflix would probably be paying closer to $1 at their scale.
Okay. Do you think Netflix actually pays $90?
So probably not 90, but I do know that most industrial CDNs are in the $100 to $200 range. I'm sure Netflix they're savvy, so they're maybe in the 30 range, but probably not 1.
Yep. No, I recently saw DevOps at Netflix talk, so I can answer. Their main strategy is they go to as many residential ISPs as possible and offer to host their data storage directly with them, so that the ISPs wins by not having to use their upstream to get Netflix data, and Netflix wins by having faster service to their customers. So they try to host it as close to their users as possible.
Interesting.
And that's their own setup.
Did they put a cost on that?
I don't know. It was more like the infrastructure is they don't use they have their own CDN essentially, and they look at where their data is being consumed, and they talk to the ISP saying, hey, we'd like to put this storage box there. Will you let us?
That sounds like something that would be very difficult for a distributed network to do effectively. But I don't want to dive into that right now. We spent a lot of time on price, and we should probably move on. So, David, you mentioned recover from seed a little earlier, which I know is a feature you're very excited about. Do you have any other key management or protections for your users here?
I don't want to say no, but because I may have misunderstood the question. But basically, the model on Saya is that you need your seed that's how we form contracts. That's how you find your money on the blockchain. And then from your seed, you can recover any snapshot that you've made, any data snapshot, and those snapshots can cover up to today 20 terabytes of data. As we continue building, that number will grow exponentially.
Okay, so the seed is a master key to everything you've stored, essentially.
Yes.
Okay. Aron and Sam, have you given much thought to key management and how developers interact with this?
I could say no. We started as being part of the Go Ethereum client, so we pretty much inherited their exact key management system. We're likely to, I'm assuming that the entire space is going to move to Clef, which is Go Ethereum has taken the key management, has made it a separate module, so that the part that deals with all the peer-to-peer networking is separate from the signer, and they're sending a signing request, and that allows programmatic rules for when it will sign and all kinds of stuff. But that's not our project. We're sort of leaning on the Go Ethereum team for that. There's another thing we can do when we talk about your own private data, so how it is encrypted, and how you generate that key and how to recover that key. That's a sort of independent consideration, or computer scientists say orthogonal. So but we have a system of encrypted uploads whereby unless you have a certain reference to the encryption of the root chunk, you won't even be able to determine anything about the file structure. And presumably you could do the same thing where you store the root hash of whatever you want in a Swarm feed or even on the Ethereum blockchain if it's important to you, and keep the encryption phrase as like a sequence of seed words, and then that would allow you the same kind of guarantee of being able to get your files by just knowing a seed phrase.
Okay.
But it's on, Swarm. It's a layer above in some sense.
Yeah, I think that's probably a fair description of what Saya is doing here, is relying on the chain's availability to rebuild your files.
Yes.
Okay.
You need the blockchain to recover
Yeah.
your snapshot.
You need a full node.
If you have access, if someone is willing to scan the blockchain for you, you don't. And that is still can be done trustlessly. So basically, we need a way to recover the file contracts and the IP addresses of the hosts that have the file contracts. And the way we've set up our recovery system is that you can actually give an identifier key to like an Explorer node or some other server, and they can use that identifier key to figure out which contracts belong to you and what the corresponding IP addresses of the hosts are. And then that identifier key is not good for anything else. It can't be used to spend money, can't be used to decrypt data. So you don't necessarily need a full node. However, we always recommend a full node.
Okay. Could that server censor contracts?
Yeah, the server could choose to send you old contracts or exclude contracts from the non-evil hosts. So that is a risk.
Kind of standard blockchain-like client security model.
Yes.
Okay. Sam, have you guys given a lot of thought to?
So for peers, I could say no. But from the point of view of users in the network, we see the network mostly for use in public open data sets. So things like websites where you want everybody else to be able to access it. And I would actually argue that decentralized storage is probably not a very good place to put things like, I think it was mentioned in the introduction, encrypted copies of your bank statements. And the reason for that is you're spreading the data around to many, many people. And eventually that encryption might get broken. So if I just sniff on the network and I listen to all the data that's being added to it and I store it for 40, 50 years, then those bank statements could be public. And I think that's something as an industry we kind of have to work. We have to pretty strongly consider this. Like, there isn't enough consideration, as far as I'm aware, for what happens when the encryption breaks.
Okay. So, honestly, I don't think like AES breaking anytime soon is a real risk. But I think your point that Arweave is intended for public data sets is kind of well taken. If you want to encrypt things, it's left up to you, the user.
Yeah, exactly. You can use whatever kind of scheme you like.
Which I think really simplifies the incentivization and security model. Yeah.
Clearly.
Yeah.
Like the publicly available data, like the DApp that I demoed earlier, that is of course not encrypted, and the more people access it, it'll just stay alive in the network. Mm-hmm. And we don't need to deal with paying for long-term storage and playing all those incentive games. So the hard thing is how to make sure a file is available in 10 years' time that nobody wants to access, so nobody's paying for access.
Right. So in Arweave, things are paid up front for 10 years or 10,000 months or whatever it is. In Swarm, you have to ensure that the reference to that file stays around and that somebody is paying for it.
So there's different ways to ensure the long-term persistence of a file. And we're still experimenting with different methods, so I don't want to highlight this is the one we're going to use because there's a few. But for DApp data and popular content, the bandwidth incentives are enough because every node is incentivized to constantly cache stuff that was being requested most recently, and once stuff stops being requested, it moves to the bottom of the queue where it's garbage collected. Now for other storage, we do a paying upfront, but that payment is locked and can only be unlocked over time by supplying a proof of custody to show that you still have the file, together with the negative incentive that if you don't supply a proof of custody and somebody accuses you on the blockchain and you cannot provide a proof, you lose a stake that you put up in advance. So it's those two sides that deal with the long-term storage incentive, yeah.
Okay, interesting. All right. Okay, so we touched on this for Psi already. Overall capacity is what, David?
Overall capacity of currently online storage is about 2,000 terabytes. But my guess is that if you were to push that limit and actually upload 2,000 terabytes and keep going, you'd find it's well over 100,000 terabytes. It's my guess.
Well,
we don't
this
know
is
this for sure.
something hard about distributed systems is we can't actually measure that, right?
Correct.
Yeah, which, Aron, you pointed this out earlier. Do you have estimates on how large Swarm is?
I don't right now, but I know our DevOps guy does.
Okay.
The idea being you start up a node, look at all the data that ends up there, and then by looking at the distribution of hashes of that data, you can estimate just the total number of chunks in the network.
Okay, I gotcha. That makes sense.
Yeah, we have a similar situation to Swarm. Like, you can't tell exactly how much data storage capacity is in the network, but you can kind of use some heuristics to essentially approximate it.
And Psi is a little bit different because hosts are publishing offers, right?
Yeah, so hosts will tell you how much, like, since you have to, like, actually request the host, you have to manually form a contract with them. So the host will broadcast, like, I'm here, I have this much data, and this is my price and whatever. And so we just, to get our metrics, when we say there are 470 terabytes on our network, what we're doing is we have a little polling thing that just asks every single host, how much data do you have? And then we add it all up. And can the host lie? Yes. Have they? No. If they start to lie, we'll be sad, and then we'll have to drop our metric.
Please, nobody, don't go home and do that.
At some point, it's inevitable that this metric will become unreliable, but we've made it 5 years, so let's keep going.
5 years, and
Use
it's gonna break in about 2 more weeks.
Proof of capacity or something to actually get them to prove it at some point.
Yeah, so we've looked into doing proof of capacity, and we've decided that it's just too expensive to be reasonable, and it adds overheads to the hosts, and we would, I think we would rather drop the ability to know the real capacity than force hosts through a proof of capacity scheme.
Typically, proof of capacity schemes require writing out the entire drive. Yeah, which is an expensive process.
Yeah, although you could make it part of the proof of work. This is something
Well,
we've been thinking about, because then, as part of the proof of work for keeping the blockchain going, you're also getting a serious estimation of how much data storage capacity is in the network.
here's additional disclosure time. I'm also an advisor at Chia, which essentially works on a similar proof
Nice.
of. I don't know what they're calling it this week, but a similar consensus system based on capacity and time. No useful file storage because you have to give that up to build consensus. Okay, so moving on there, what are you looking to be in the future? We've talked a little bit about Arweave's long-term goals of being a public archive. Is there any specific thing you'd like to see on it?
Yeah, so much. I mean, what we really care about is getting a record, like from a personal point of view, and I think what motivates most of the team, is that we get a permanent record of history as it happens that's verifiable, time-stamped, and immutably, essentially censorship resistant. So that's like the key thing from our point of view as, let's say, from a non-business side. But there's also a whole bunch of other things you would want to put on the system that are, commercially focused.
Right, if it's going to stay around forever. Yeah. Aron, what do you see Swarm being in 5-10 years?
So we see it as an integral part of what we're calling the Web 3.0. So right now, a lot of the new Ethereum and other smart contract-based apps, they run on somebody's server, and they probably use Infura or some centralized service to interact with the blockchain. So it's not quite there yet. The idea is once you have an application running on Swarm, let's say it's a social network or what have you, the idea that it will stay alive as long as there are still users who care about it and cannot be turned off, that's an important one. The other thing is I can just look at the hash of your app right now and save it under my own name, and I've forked it, but I am still have the same content, the same users, the same communication channels. It's just like you can fork WordPress code, but you can't fork WordPress.com. In this Web3, you can actually fork a live network and really compete on the features, because people could interact with the same people through your version of this app or through the other one. And that could bring the same level of innovation to pre-existing networks that open sourced it to code. And it means you can have huge networks without this specter of someone controlling it or being able to shut it off or censor it. Like so this real decentralized serverless web, that's sort of my personal vision for what this is about.
A home for applications rather than just static files.
Definitely for dynamic content. So we do allow message routing within the Swarm network as well. So you can send a message from a particular node to a particular other node. So we allow messaging protocols and chat to be developed. There's people who are working on streaming, which of course you don't know in advance what your content hashes will be. So how do you do streaming content? Mutable data, there's an interesting thing where instead of storing the hash of some content on the blockchain, you store something else which generates a deterministic sequence of addresses, and these are addresses within the swarm you can poll and then see if somebody's left a signed message there for what the current hash of the actual content is, so we can allow far more dynamic content. Right. So it's generally the entire Web 2.0 recreated without servers. So from dynamic web apps to personal encrypted storage, it all has to live somewhere.
Right.
And we want to be that network.
It's a very ambitious project.
Oh, yeah.
David, where do you see Saya in 5 years?
I don't know about 5 years, but maybe in 20 years, I would say all data in motion and all data at rest will be somewhere under the Saya protocol umbrella.
So everything.
Yeah. And like,
got it.
You know, as we develop the Saya protocol, we keep finding more and more interesting ways that we can do things. For example, something like a VPN over the Saya network would be very natural to implement. Or like we used to think in 2016 that doing something like YouTube on Saya would be extremely challenging, or even just like a blog on Saya would be extremely challenging. But in the past 9 months, we've actually found a very comfortable, secure way to achieve that. And of course, this is something we're excited about. But I think, yeah, the combination of its speed, its cost advantage, and its decentralized durability means that any data that you're not actively doing computation on is a target for our network.
Okay. I think no one's ever accused blockchain projects of having narrow scope or vision, but it sounds like the plan here is to be everything for Swarm and Saya. Yeah, that's okay, great.
Everything permanent for us.
Everything permanent. So I know we've touched on this a little bit. David, you've talked about latency and throughput compared to Amazon. You said in your slides that you were targeting 50 milliseconds, and we're at about 1.5 seconds right now?
Yep. And we have not done even some very basic protocol level optimization yet. And so I think we can get down from 1.5 seconds to well under half a second, I think, with just looking at it and doing some basic optimization. Getting to 50 milliseconds will definitely require a little more elbow grease, but we can get pretty close to that without too much work, I think.
And to be clear, the 1.5 seconds is time to first byte?
Yeah, time to first, I'd say 4 kilobytes.
Okay, from first chunk. From when I make the request to when I receive the first chunk is 1.5 seconds?
Yes.
Okay. Aron, how we saw it earlier. It was pretty snappy. What do you know, time to first byte?
I can't because it varies a lot. So what really the most important metric is how recently did somebody else access that content. So if we are a Swarm node and you've been connected for a while, you've got your 20 peers or whatever it is, you will be polling them for data, and they will poll their peers. And the closer it is, the faster you will get it. So popular data, which is widely cached, goes really snappy. Whereas other data, it starts slow, becomes faster over a while. Same as when you do a BitTorrent download, it starts really slow and then you get this rush. So we have similar patterns, but because I was working on those slides yesterday and I was trying it out on various hosts, it was kind of cached right now, so you saw it was almost instant. One point about latency, if latency is important to you, what you can do is if you have your 100 chunks of a file, but they're part of some 150 that in an erasure coded set, What you can do is you're paying more, but you can request all 150, and then the first 100 of those give you the data. So you can pay with extra bandwidth to get lower latency. So it kind of depends there on your usage.
Right. And Sam?
Yeah, I mean, we just copy BitTorrent, which I guess, going back to the introductory talk, is just using the kind of battle-tested approach. Yeah. Like, it's very clear that this works. But I'm actually kind of interested in these pay-for-retrieval schemes. It's extremely difficult to verify that a transfer has actually happened on the internet. This is something like a Filecoin has open spec, so you can kind of go look at it on GitHub. It's kind of interesting, the discussion about this, because they basically say, like, we don't verify. But with SIA, you guys have a thing,
so
right?
we have a very simple way to determine whether or not we've received the data, which is that if we received it, then we'll go ahead and pay for it. So what we do to unpack that a little more is we'll pay the host for up to some amount of data, usually 4 megabytes. The host will send us 4 megabytes, and then we'll pay them for the next 4 megabytes. If at any point 4 megabytes on the SIA network is extremely cheap, not worth mentioning the amount of money that's at risk. And if the host
at $90 per terabyte, a megabyte is something like 0.009 cents.
Yeah.
In that neighborhood. Maybe a little less.
That seems like the same as we do. You're repeatedly doing dealings. You're repeatedly doing dealings with the same host. That's why I mentioned like the discipline of repeated dealings. You're connected to the same peers, and you're going to do business with them for a longer period of time. And there's a constantly data going one way, and you'll start accruing debt, and then so the thing is, we can set the interval at which you expect payment. So when it's a new peer, you request them to pay relatively frequently, but after a while, once a day might be enough.
Right. So real quick, we've talked about Swarm and SIA saturating bandwidth. Is Arweave, saturating people's download bandwidth right now?
Download bandwidth, if there was that much demand for download bandwidth, yeah. Mm-hmm. Just like BitTorrent. But this chunking mechanism definitely seems like the only way that anyone has found to actually do this in practice. It's definitely the right way to do it. But it, if I'm understanding correctly, does introduce this latency issue, right? So if I send you 4 megabytes, and then we have to reconvene, right, and start again, then every 4 megabytes we get the latency of reconnection.
You can retrieve all of these in parallel, and for most use cases, it's acceptable to get chunks in any order.
But you can't do it in parallel because you have to make sure that the payment is happening.
Right? You just do a bunch of pipelining, and then your exposure goes up by some factor. But it's in terms of speed, it's like not an issue.
Yeah. Well, a payment via a channel is like a few hundred bytes tops, and we're talking about transferring 4 megabytes. So this is negligible overhead for any payment system.
Yeah, it's negligible transfer, but it's the latency that's the problem, I think. But yeah, I just hope as an industry we come up with like a better solution to this, because it's kind of a complex problem.
Definitely, but I think that it's likely that the rules of the universe forbid transfer proofs.
Yeah.
Moving on from there. Okay, so UX real quick. We've talked about this. David, you download a full node, you run a wallet, there's a user seed, and an API for your full node.
That's roughly correct. I would say if you want to be a true sovereign individual of the SIA network, you need a full node. I think that's true of any blockchain. And I would say if you want to get set up that way, it's probably going to take you a full day. On an SSD, the blockchain will come down in maybe 4 or 5 hours, and you have to set up contracts. And this is something we're actively working on. We want to make it one step, so you just queue it up, spend like 60 seconds configuring it, and then it'll run in the background and start uploading data when it's ready. But right now, it's more hands-on, maybe like half a day.
Okay, and one of the critical parts of user experience is browsers. Most of us do our interaction with files in a browser. Does SIA work from a browser? Can you retrieve files today?
From a file browser or a web browser?
From a web browser.
SIA today cannot get, because everything's paid. So we don't have a good way to deliver files to a web browser. I would say we're about a year out from being able to do that extremely well, at which point we will start doing BD with Netflix.
Okay, so great. Sam, I know you said already that it works in a browser. It uses HTTP and JSON. What steps do people need to go through to upload things to Arweave?
So upload is mostly done through web applications that are themselves served from the Arweave. So you're essentially just loading in a wallet, signing a transaction, sending it to the network through HTTP. But we see the core, well, it is a protocol. It's just offering you, as a developer, typically a service that you can't get elsewhere. And you can embed that service into many, many different applications. So we care more, I would say, about developer experience, at least in the short term, than end user experience. That's kind of we need to enable the developers to make good end user experiences.
I think that's a common theme among decentralized storage projects.
For sure.
Aron, we saw the download experience earlier. Putting a name into a browser is pretty nice. Where are we on upload for Swarm?
Well, everything goes through the HTTP API. So to upload, it's a simple post. So if on that photo album I'd have clicked the plus, add a picture, upload, it would have done post, and it would be there.
Right. And where is this HTTP API? Is
so
it
there's
on
a local,
okay.
Right. So I did one that was on my server, but you'd presumably run a local version of a Swarm node and you will talk through it through a local proxy. Having said that, we are, of course, aware that not every device can host a full Swarm node, and we are working to develop we don't even call it light node, but adaptive node, where you can adapt which of the Swarm services you want to host and participate in, depending on whether you're on your phone or laptop or what have you. But ultimately, it should just be the HTTP API. Just post and get is really all we need. I'm kind of hesitant when I answer because I know there'll be all kinds of complications for once we add payments and proof of burn and all these different things. But since we don't have them live yet, I don't need to.
Don't need to worry.
I will add, before we added payments, we did support web browsers, and then we added payments, and it became challenging again. But we know how to fix it. It's more work.
Is the main problem here integrating with user wallets in the web browser?
Yeah, the main problem is the host isn't going to serve data unless they receive some monetary compensation, and doing that from a web browser requires extra steps, either an extension or somehow talking to localhost or having the server pay on your behalf. And that's the plan for CDN, is Netflix would pay on your behalf, give you a token through a JSON object that the host can then verify. It's oh, okay, this is paid for.
In our case, if you have a local node running, it will handle the payments for you, so you could still easily do everything through the browser interface. It's when you want to do it via a light node, then you have to, we have to figure out the details there. But yeah, there's definitely the one part which is interacting with the HTTP API for the content, and then there has to be another component somewhere handling the payments.
It's hard enough building a storage system. Building a storage system and a light wallet in a browser is a whole other problem.
Correct. Yeah. But having said that, there's more and more browser vendors who are interested in getting into this space, and we've seen from Brave and Opera their willingness to integrate, Ethereum wallets and other wallets directly into the browser. And we have also been talking to, I think it's Opera specifically, to natively allow BZZ protocol in Opera to talk to the Swarm node. So there's definitely movement in that direction to integrate all that.
It's interesting. Okay, so we're mostly through the set questions. We have about 5-10 minutes for lunch. I think we can, before lunch, 5-10 minutes before lunch. We have more than 5 minutes for lunch, don't worry. I think we can open it up to a few audience questions. I know Mark over there has been sitting on his for a little while. Dave, would you mind passing him a mic real quick? Okay, we can repeat it too. Oh, there we go.
So a lot of your guys' systems depends upon challenge response to prove that the storage is there. And there's kind of two assumptions which is, well, that means somebody has to have an offsite copy of the data to even generate the challenge. And, okay, and then the second question is, same thing with that is, if a user doesn't have an offsite copy to generate the challenge, then who's going to do it on their behalf?
So we don't actually do this in our system, but you definitely don't need an offsite copy in order to generate the challenge. So for example, a really simple system is, say, you store a Merkle root of a piece of data, and then you say, okay, give me chunk 10, 50, 125, and then the person has to provide those chunks, and part of the Merkle path back to the root. And then you can verify this without actually having access to the data.
So this is a nice advantage of primarily storing public data, right? You don't need to preserve confidentiality through this challenge response process.
Yeah, but this is just the most basic system you could build that does that kind of thing. You could make it more extensive if you like. Yeah, you guys actually do this in your system, so.
You can generally poll for specific parts of a file together with a Merkle proof that it's part of that file. That's also how we do partial reads in larger video files. But you could also, when you hand over your file for storage, you can prepare a sequence of challenges that are much, much smaller than the file size, which is like, give me the 30-second chunk concatenated with this salt and prove that you have it. So you only need to, the challenge response only requires some hashes, so it's very small. But because it's a salted challenge, you know that it can only be generated by your counterparty if they have the actual data. So that part is actually, and it can be strung together to get an audit of a huge file collection where I send out one hash and the answer is one hash, and there's a proof in there somewhere that 30 gigabytes is available. That's how far you can push this game if you want.
Merkle constructions for this require like a large, heavy pre-processing step, right? Yeah. Logarithmic in the file size?
Yes.
Yeah. David, how do you handle this?
Yeah, we do probabilistic Merkle proofs. So in terms of creating the data, it's close enough to linear that we just can consider it to be linear. And then challenges don't have to be issued by anyone in particular. The blockchain actually has a set height at which it will issue its own challenge. And basically, so the blockchain has a Merkle root, and it's like, okay, give me piece 980 of the file and prove it's part of the Merkle root. So no one needs to be around. The renter can disappear. And the challenge will still be delivered to the host.
Merkleize everything.
Okay.
Yeah, although that does kind of introduce scalability problems, right? Like, if you're, say you're going to put a web on this thing, you're going to put trillions of files, then is the blockchain really going to issue a challenge for each one of those trillions of files?
Does it need to?
Well, actually, Filecoin, interestingly, yeah, they just take the approach that, like, if you put a file inside it, it's your responsibility to issue the challenge, and then if they fail to respond to your challenge, then you ask the blockchain to do it.
So
Sia, what's the...
you
have tickets in the German metro. It doesn't need to check it for everyone, but still everyone does it because if you randomly check it.
Like a random polling, yeah.
So it's not really correct to think about files on Sia, and more correct to think about file systems on Sia. So as one user, I have 50 contracts, and if I have 10 trillion files, that's going to be spread out through 50 contracts. And so I can cover my whole data with just 50 challenges.
So blobs instead of files.
Yeah.
Yeah. Okay. Sean, how's it going?
Hey, James. Hey, David. So can you talk to me a little bit about high orders of scale with decentralized storage networks and your kind of solutions to them? At Storj, when we reached 150 petabytes, we had to like scrap the system, start from scratch. So I'm just curious about your thoughts and your architectures on high orders of scale. And I'll also add the answer to your Netflix cost thing if you want to know.
I'll take the answer to the Netflix cost thing.
So there's a bit of like it completely blew my mind when I found this out, but there's a bit of a dark market when it comes to bandwidth. There's like
dark fiber.
Yeah, there's like $90 a terabyte for public pricing, but when you're transacting like petabytes and petabytes, the cost actually goes down by an order of magnitude or two. So they're paying a couple dollars per terabyte.
Okay. Now to answer your question, high orders of scale on the Sia network. We deliberately architected the Sia network to have all the complexity in the client. So the protocol we made as simple and as basic as possible. And I shouldn't say basic, I should say as fundamental as possible. If it wasn't strictly necessary in the protocol, we pushed that thing to the client because you can iterate on the client a lot faster than you can iterate on the protocol. So the SIA architecture is a very carefully structured fundamental set of base blocks that has virtually unlimited scalability. You're talking hundreds of quintillions of terabytes can be handled by a single file contract. And so the high order scalability of the protocol itself is, for all practical purposes, unlimited.
So doesn't that require, as you scale up, aggregating more and more files under each contract? Because the number of contracts the system can handle is essentially set.
Yeah, so the system can handle a finite number of contracts as regulated by the block size, essentially. And so that does mean as you scale up, each contract needs to handle more and more data, and then that's where the client-side complexity comes in. The client is responsible for figuring out how to manage that large amount of metadata.
So you kind of see an ecosystem of aggregators here, taking many different users' files and putting them under contracts?
No.
No.
We have a different idea for blockchain scalability. It's way too early to really talk about this, but essentially for file storage, these contracts don't need to be global. We don't need every user to be on the same blockchain. We just need every blockchain to be sufficiently secure to store the user's data. So we might start automatically splitting blockchains. And so there'll be separate chains, separate currencies, separate proof of work algorithms. But because we can use Lightning Network and everything, they're all super interoperable. And it doesn't, Handwave, it works out really well.
Great. And that's how you store everything ever, move all data.
Yeah.
Yeah, okay.
I mean, I just want to jump in on that note, that there's another side to Swarm, which is the original mission also included the ability to store the Ethereum blockchain. And we are working with the Trinity client specifically for a proof of concept. And the idea is we no longer need full nodes that have everything and light nodes that have nothing. We can just have a whole bunch of Swarm nodes, and as long as all the blockchain data is available, the entire state is available in the Swarm, each node is like halfway between light and full, and it completely flexibly allows for the Ethereum state to grow beyond the capacity of a single node and still be secure.
All right. So I would love to take more questions. We do have to break for lunch, and the panel will not be continuing afterwards. I know it feels like we're on all day, but we're actually not. Do each of you have like one last sentence, like any closing remarks here? Anyone? No? No?
Yeah, I think that as a society, we have substantially underestimated the systemic risk associated with piling centralized services on top of each other, and that it's like your moral duty to move your data onto a decentralized platform, and all your other stuff too. Like we should see it as a moral imperative to like proactively decentralize ourselves.
Okay. Aron, last thoughts?
I agree with that sentiment. My take is that we got to where we are not based on malice, but because of the way the incentives we figured out for the web. Google didn't start out wanting to be a surveillance company. Facebook didn't want to be a surveillance company, but they wanted to make money. And the only business model we've discovered on the web so far is to collect a lot of data and sell that. And the way we require these, so you've got these benefits of scaling that are built in, and you've got these benefits of surveillance. Now, what we are doing in this blockchain space, on the one hand, we are architecting for new kinds of web applications that do not have these central points at all. That's what decentralized storage and decentralized web apps is all about. And on the flip side, we now have programmable money and micropayments that could allow all kinds of new business models that no longer require someone to try to get their hands on all that data. And so that really is the vision. The vision. Get away from this surveillance capitalism by both making it harder to observe and by making it no longer an economic necessity to observe everyone.
All right. Sam?
Yeah, and I would just agree with both of those points, but also just add that now is the time to actually build and ship and get people to use these things. Like, we've been talking about this stuff since basically 1992 on the cypherpunk mailing list. Like, all these ideas have been out there for a very long time. It's time to actually get people on board.
Right, and on that note, one of the questions that I wanted to ask but never got around to is how each of you compare to Mojo Nation. But it's a deep cut. All right. Anyways, thanks everyone. It is time for lunch. I'm gonna let you get out of this lecture hall.
Thanks.